One line added to stochastic gradient descent gives you roughly 10 times faster convergence on hard landscapes and amplifies the noise by about 2.3. Here's why we use it anyway. This is the Forward Pass AI Optimizer series, one optimizer per episode, depth over breadth. Episode 4 was Vanilla SGD, the foundation. Episode 5 is Momentum SGD, what it changes, what it costs, and why it's still the right trade. Momentum. Recall Vanilla SGD on a ravine, a landscape steep in one direction and shallow in another. Each step, SGD bounces across the steep walls while barely moving along the shallow floor. The gradient is large where progress should be small, and small where progress should be large. Most of the work goes into oscillation, not descent. SGD has no memory. It can't tell a consistent descent direction from a gradient that keeps reversing. Momentum solves exactly this by giving the optimizer a memory of where it has been. Here is code A. Momentum SGD as a two-line diff from Vanilla SGD. First change, initialize a velocity variable to zeros. This is new state that SGD never had. Second change, each step, set velocity to beta times old velocity plus gradient. This accumulates a weighted history of past gradients. Third change, step opposite the velocity instead of the bare gradient. Same loop structure, one extra variable. That is the whole mechanism. Running code A from a starting point of 5, with alpha equals 0.1 and beta equals 0.9 for 50 steps, prints a value very close to 0. The optimizer reached the minimum of f of the variable x equals 1/2 the variable x squared. The consistent downward gradient compounded step after step velocity built, and the parameter converged faster than plain SGD would on the same landscape. Beta is the inertia retention dial. It controls how much past velocity survives into the next step. At beta equals 0, nothing carries over, plain SGD. As beta approaches 1, the velocity decays more slowly and the memory grows. The effective memory horizon is roughly 1 over 1 minus beta. In other words, it's the number of past steps that still have meaningful weight in today's velocity. At beta equals 0.9, roughly 10 steps. At beta equals 0.99, roughly 100. To see what the velocity actually contains, suppose the gradient is the same constant value g at every step. Unroll the recursion one step at a time. This step's g plus beta times last step's g plus beta squared times 2 steps ago, and so on. Factor out g the bracket, 1 plus beta squared, continuing without end, is a geometric series. A geometric series with ratio less than 1 sums to 1 over 1 minus the ratio. Here the ratio is beta, so the bracket sums to 1 over 1 minus beta. In other words, a consistent gradient of size g produces a steady-state velocity of g divided by 1 minus beta, at beta equals 0.9, that is a 10 times amplification of the consistent direction. Real mini-batch gradients are not constant. Decompose each step's gradient into 2 parts, signal plus noise. Signal is the true gradient consistent in direction across nearby steps. Noise is the sampling error. 0 mean on average and uncorrelated from one step to the next. The velocity will process both simultaneously, but it does opposite things to them because their statistical structure is different. To see what happens to the noise, we need one rule to hold. When you multiply a random variable by a constant c, the variance scales by c squared, not by c variance of c times the variable x equals c squared times the variance of the variable x. The reason, variance measures spread, and multiplying by c stretches the spread linearly. But variance is spread squared, so the constant enters squared. Hold that rule for the next block. Now the noise path. The accumulated noise in the velocity has the same structure as the signal. Current noise, plus beta times last step's noise, plus beta squared times 2 steps ago. Noise is a random variable, so we ask about variance rather than value. Apply the rule from the last block. variance of beta times last step's noise equals beta squared times the variance of last step's noise, the constant beta enters squared. Each noise term has the same variance, call it sigma squared, so we factor it out, sigma squared times the bracket 1 plus beta squared plus beta to the fourth, and so on. Notice the powers, this is beta squared as the ratio, not beta, that is the rule from the last block paying off variance of c times the variable x squares c, so every beta becomes beta squared inside the variance. The series sums to 1 over 1 minus beta squared, so the noise variance in steady state is sigma squared over 1 minus beta squared. At beta equals 0.9, 1 minus 0.9 squared equals 0.19, so the noise variance is roughly 5.3 times the original variance. The noise standard deviation. The square root of the variance grew from sigma to the square root of 5.3 times sigma, which is approximately 2.3 times sigma. Compare what happened to signal and noise. The signal magnitude grew from G to 10 times G, a 10 times amplification. The noise standard deviation grew from sigma to 2.3 times sigma. Both grew. The EMA did not shrink the noise in absolute terms. This seems to contradict intuition. If averaging filters noise, shouldn't noise decrease? The answer is yes in the mean. The expected value of the noise is still 0. Averaging drives the mean toward 0. But variance doesn't cancel under addition, it adds. Each term's noise contributes its variance to the total, independently, without cancellation. So the absolute noise size grew, even as the mean stayed at 0. What matters is not the absolute size of the noise, but how it compares to the signal riding on top of it. That comparison is the signal-to-noise ratio. Signal-to-noise ratio before momentum. Signal magnitude G divided by noise standard deviation sigma after momentum. Signal is 10 times G, noise standard deviation is 2.3 times sigma. The SNR becomes 10G divided by 2.3 sigma, which is the original G over sigma multiplied by 10 over 2.3, roughly 4.4. In general, the signal amplification is 1 over 1 minus beta, and the noise standard deviation amplification is 1 over the square root of 1 minus beta squared. The SNR boost is signal amplification divided by noise amplification, 1 over 1 minus beta, divided by 1 over the square root of 1 minus beta squared. Simplify using the factorization, 1 minus beta squared equals 1 minus beta times 1 plus beta, taking the square root. Square root of 1 minus beta squared equals square root of 1 minus beta times square root of 1 plus beta. Plugging back into the ratio, the 1 minus beta in the denominator and the square root of 1 minus beta in the numerator cancel, leaving the square root of 1 plus beta divided by 1 minus beta. At beta equals 0.9, the square root of 1.9 over 0.1 equals the square root of 19, roughly 4.4. Even with noise growing in absolute size, the signal-to-noise ratio improved by 4.4 times. This velocity recursion is an exponential moving average, and EMA and its geometry explains the SNR result. Here is the geometric picture. Imagine a sequence of gradient vectors accumulated by the EMA. On the left, vectors that all point roughly the same direction. When summed, each one reinforces the last. The resultant grows linearly. 10 pushes in the same direction produce 10 times the displacement. On the right, vectors pointing in random directions. When summed, they partially cancel. The resultant grows with the square root of the count, not linearly. 10 random pushes produce only about 3 times the displacement of 1. Linear growth in the numerator, square root growth in the denominator. That asymmetry is the entire mechanism behind the SNR improvement. Recall that V star G divided by 1 minus beta is the steady-state velocity, the value this EMA converges to under a constant gradient. Understanding the SNR improvement is only half the picture. The other half is what this amplification means for how you set your hyperparameters. Alpha and beta are not independent dials. under a constant gradient g. The step taken each iteration is alpha times the steady-state velocity. Define the effective learning rate as alpha divided by 1 minus beta, the actual step size per unit of gradient. In plain terms, the effective step is larger than alpha alone whenever beta is greater than 0. At beta equals 0.9, alpha f equals 10 times alpha. If you copy alpha from a working SGD run and add beta without adjusting, you have silently multiplied your step size by 10. This is the most common instability, misdiagnosed as momentum being unpredictable. The fix is straightforward. When you increase beta, scale alpha down by 1 minus beta to keep alpha f constant. The table shows 3 equivalent alpha-beta pairs that all produce the same effective learning rate. Some libraries use a dampened parametrization, velocity equals beta times old velocity, plus 1 minus beta times gradient. This decouples alpha from beta at the cost of losing the 1 over 1 minus beta amplification. Atom and RMSprop use this form internally. We'll return to those forms in episodes 7 and 8. For now, let's see the beta sweep make the theory concrete. Here is code the bias B, a sweep across 4 values of beta on the ravine landscape. Same starting point, same learning rate alpha equals 0.013, same 50 steps. Only beta changes. Beta equals 0, plain SGD. The grade trajectory zigzags across the variable x direction, barely advancing toward the minimum. Beta equals 0.5, mild smoothing. The green trajectory is less erratic, the oscillations are damped. Beta equals 0.9, the blue trajectory arcs cleanly toward the minimum. This is the signal compounding regime from the derivation coherent gradients compound, oscillations cancel. Beta equals 0.99, the red trajectory overshoots. The inertia carries the optimizer past the minimum before the gradient can turn it. Same learning rate, too much memory. The regime has changed again. Beta equals 0.9 is not universally best. It depends on the landscape. The sweep makes the regime change concrete. That overshoot at beta equals 0.99 points to the most common refinement of momentum SGD, Nesterov accelerated gradient. Here is code C, Nesterov accelerated gradient as a 2-line diff from code A, the momentum SGD implementation we built in block 05. First change, before computing the gradient, compute a Luckake position, current position minus alpha times beta times velocity. This is where momentum will carry you on the next step. Second change, evaluate the gradient at the Luckake position, not at the current position. That's the only other change. The rest of the update is identical to code A. The geometric intuition. In code A, momentum commits first and corrects after. In Nesterov, the optimizer peaks where it will land, evaluates the gradient there and corrects before committing. The gradient is computed at the expected next position, not the current one. Libraries implement this through the Stochastic rewrite, a change of variables that gives the same update without a separate forward pass. PyTorch Nesterov equals true flag implements that form. Running code C from starting point 5, alpha equals 0.1, beta equals 0.9, 50 steps. Both the Luckake form and the Stochastic form print a value very close to 0. Both converge to the same minimum, the same algorithm expressed 2 ways. The Luckake form is geometrically transparent. The Stochastic form is computationally efficient. Same answer, different arithmetic path. Momentum has 2 limits worth naming situations where it can't fully solve the problem on its own. Limit 1, overshoot near sharp minima. When the landscape curves sharply, when curvature changes faster than the velocity can decay, inertia carries the optimizer past the minimum. You saw this at beta equals 0.99 in code the bias B. No single beta eliminates both oscillation and overshoot simultaneously on a curving landscape. Limit 2, a single beta applies the same temporal smoothing to every parameter, but parameters in a real network can have very different curvatures and gradient scales. Momentum smooths in time, it does not adapt to the space of parameters. This raises the natural question: What if the smoothing were per parameter, not just temporal? What if each parameter had its own effective memory, tuned to its own gradient scale? That question opens episode 6. The mental model. Vanilla SGD forgets each gradient the instant it is used. Momentum accumulates a velocity, a weighted sum of all past gradients, with older ones down-weighted by powers of beta. Coherent gradients, those pointing the same direction, compound. Their sum grows linearly. Incoherent gradients, the noise partially cancel. Their standard deviation grows with the square root of the count. That asymmetry is why the signal-to-noise ratio improves. The SNR boost formula, the square root of 1 plus beta over 1 minus beta. At beta equals 0.9, roughly 4.4 times the original signal-to-noise ratio. Alpha and beta are coupled. The meaningful dial is the effective learning rate, alpha divided by 1 minus beta. Always scale alpha down when increasing beta. Nesterov is a two-line look-ache. Evaluate the gradient where momentum will carry you, not where you currently stand. Same algorithm, slightly smarter gradient placement. One line added, one extra variable, and the optimizer can now distinguish a consistent descent direction from noise. Episode 6. Adagrad. Instead of smoothing gradients in time, Adagrad scales each parameter by the accumulated sum of its squared gradients, a per-parameter memory of how large the gradients have been. Episode 7, RMS Prop, fixes Adagrad's monotonic decay problem, the learning rate that only ever shrinks. Episode 8, Atom, fuses temporal momentum with per-parameter scaling into a single update. Momentum is not superseded, it gets fused. The optimizer story builds, it doesn't replace.